What if the largest galaxy ever discovered is not a galaxy in any sense we normally understand, but a structure so vast that the word galaxy begins to fail before the measurements do? For most of human history, the Milky Way was not seen as one galaxy among many. It was the universe itself. A river of stars stretched across the night, assumed to contain everything that existed. Even after modern astronomy revealed that our Sun was only one ordinary star inside a much larger stellar system, the Milky Way still retained a strange psychological status. It remained, in some quiet way, the boundary of what felt imaginable, our cosmic home, our largest frame of reference. And that frame already pushes against comprehension. The Milky Way spans roughly 100,000 light years across, though some measurements place its outer structures much farther. Numbers like that are easy to recite and almost impossible to feel. A beam of light, moving at the fastest speed allowed by physics, needs 100,000 years to cross from one side of our galaxy to the other. When that journey begins, entire civilizations can rise and disappear before the light reaches its destination. And yet, what makes the Milky Way difficult to grasp is not just its size, but what fills that size so sparsely. Our galaxy contains hundreds of billions of stars, but those stars are not packed together in a dense luminous swarm. They are separated by immense gulfs of emptiness. In our region of the galaxy, the nearest star lies 4 light years away. 4 years for light itself to make the crossing. The galaxy is less like a crowded city of stars and more like scattered islands separated by black oceans so wide they enforce isolation as a law of structure. This emptiness changes how we think about the universe. It means that even within a single galaxy, distance acts almost like a barrier between worlds. Any civilization arising around another star may exist in practical solitude, not because life is rare, but because the spaces between stars are so large that contact may be structurally impossible. The silence of the cosmos may not be a mystery at all. It may be the natural consequence of galaxies built mostly from emptiness. And this is only an ordinary galaxy. The Milky Way contains perhaps 200 to 400 billion stars. It hosts a central black hole 4 million times the mass of the Sun. It possesses spiral arms sculpted by gravity over billions of years. It is vast enough to contain more planets than human beings could ever count. And yet, in the scale hierarchy of the universe, it is not unusual. It is not an extreme object. It does not sit at the upper limit of galactic possibility. In fact, the Milky Way may be larger than most galaxies in existence because most galaxies are dwarfs. That alone should be unsettling. If what already feels incomprehensibly large is merely above average, then our intuition about cosmic scale is probably broken at the foundation. And the first crack in that foundation appears when you look toward a faint blur in the constellation Andromeda. That blur is not a nebula. It is another galaxy. A system of roughly 1 trillion stars, larger than our own, lying 2.5 million light years away. The light reaching us from Andromeda tonight began its journey before modern humans existed. You do not see that galaxy as it is. You see it as it was when our ancestors still shaped stone. Andromeda is not just bigger than the Milky Way. It is a warning. Because it reveals something simple but destabilizing. Our home galaxy is not the natural upper limit of what a galaxy can be. It is merely one example among larger possibilities. And once that realization takes hold, a deeper question begins to form. If the Milky Way is ordinary and Andromeda is only modestly larger, then what exists at the far end of the distribution? What happens when gravity is given not billions, but tens of billions of years to build without interruption? What kind of structure emerges when galaxies do not remain isolated but begin consuming one another, growing through repeated acts of merger and accumulation, until the distinction between one galaxy and many starts to blur? Astronomers found that such objects exist at the centers of massive galaxy clusters where gravity pulls hundreds or thousands of galaxies inward over cosmic time. Some galaxies do not merely survive, they feed, they absorb neighbors, they grow, and in doing so, they become something so large that even Andromeda begins to look provincial. But before we reach those giants, there is one uncomfortable fact about Andromeda itself that changes the direction of this story completely. It is already falling toward us. The Milky Way and Andromeda are moving toward one another at roughly 250,000 miles per hour. At first, that sounds like catastrophe in motion. But on galactic scales, even collisions unfold with extraordinary patience. The merger will not happen tomorrow, or in any epoch humanity will witness. It will happen roughly 4 to 5 billion years from now, long after the Sun itself has entered the final phases of its life. Yet, the significance of that collision has almost nothing to do with when it occurs. It matters because of what it reveals about how galaxies grow. For a long time, galaxies were imagined as relatively stable islands, enormous but persistent structures drifting through space. Modern astrophysics replaced that picture with something far less static. Galaxies evolve through violence. They collide, distort, cannibalize one another, and in doing so, become new objects. What we call a galaxy is often only a temporary phase in a much longer process. When the Milky Way and Andromeda merge, neither galaxy will survive in its present form. Their spiral arms will be torn apart. Their stars will be redistributed into chaotic orbits. Their central black holes will spiral together and eventually merge, releasing gravitational waves powerful enough to ripple space-time itself. Out of two great spirals, a single giant elliptical galaxy will emerge. This future object is sometimes called Milkomeda, and for a moment, it seems like the natural endpoint of galactic evolution. A trillion or more stars gathered into one massive structure, the union of two dominant galaxies, a final form. But this is where another assumption begins to fail, because even Milkomeda would not be unusually large in the deeper architecture of the universe. To understand why, you have to stop thinking in terms of isolated galaxies and start thinking in terms of galaxy clusters. Our local group contains more than 80 galaxies spread across roughly 10 million light years. It feels immense, but it is a sparse environment, a quiet gravitational neighborhood. Beyond it lie structures far denser and far more extreme. The Virgo cluster contains more than 1,000 galaxies. The Coma cluster contains thousands. These are not neighborhoods, they are gravitational ecosystems. And at the center of these ecosystems, something extraordinary often forms. Over billions of years, smaller galaxies lose orbital energy through a process called dynamical friction. Slowly, almost imperceptibly, they spiral inward toward the cluster center. And when they arrive, they are absorbed by the central giant already waiting there. One merger becomes 10, 10 become 50, 50 become hundreds. Over cosmic time, a galaxy at the bottom of a cluster's gravitational well can grow not by forming stars in the ordinary way, but by feeding on entire galaxies. This is not metaphor. Astronomers can see the evidence in the diffuse stellar halos surrounding these objects. Vast envelopes of ancient stars extending far beyond the bright central regions. Fossil records of repeated mergers written directly into starlight. These systems belong to a category called brightest cluster galaxies, or in their most extreme forms, CD galaxies. And they are unlike the spirals we know. They do not possess elegant rotating arms. They do not preserve ordered disk structures. They are immense, swollen, often spheroidal bodies of old stars, gravitational end products assembled through billions of years of accumulation. The universe did not simply make them large, it made them by letting gravity feed without interruption. And this changes everything. Because once you understand that galaxies can grow through repeated mergers at the centers of clusters, the Milky Way and Andromeda no longer look like major actors in the story. They begin to look like ingredients. Even their future merger, which feels so consequential from our perspective, starts to resemble merely one early step in a process that can continue for billions of years beyond anything we normally imagine. Milkomeda would not be a final form. It would be the beginning of a much larger possibility. And there is one galaxy in particular that forces this realization into focus. It sits at the center of a massive cluster over 1 billion light years away. Its stellar population may approach 100 trillion stars. Its diffuse halo extends across millions of light years. Its central black hole may outweigh the one in our galaxy by tens of thousands of times. And if placed where the Milky Way sits now, it would not merely dominate our local group, it would engulf it. This was the moment astronomers began confronting something uncomfortable. There may be galaxies so large that comparing them to the Milky Way stops being informative. The comparison itself begins to break. Because when a single galaxy competes not with another galaxy, but with the scale of an entire galactic neighborhood, we are no longer talking about larger versions of familiar objects. We are entering another category altogether. And this is where the idea of the largest galaxy ever found first begins to emerge. For decades, one object stood at the center of that discussion. A galaxy so extreme that it seemed to represent the upper limit of what gravity could build. Its catalog name was unremarkable, IC 1101. But what astronomers found inside that name made even the future merger of the Milky Way and Andromeda feel small. And the strangest part was not its size. It was what its existence implied about what happens when gravity is given enough time to keep going. The problem begins when a galaxy stops behaving like an isolated object. For most of modern astronomy, a galaxy was treated as a contained system. Stars orbit inside it, gas circulates through it, dark matter holds it together. Even when galaxies collide, merge, or feed central black holes, the assumption remains the same. A galaxy has a boundary, even if that boundary is difficult to define. That assumption starts to weaken when we look at systems like IC 1101. At first, IC 1101 seems to fit the classic picture of a giant elliptical galaxy. Its visible stellar body already pushes the limits of scale. Hundreds of thousands of light years across, trillions upon trillions of stars. A central black hole so massive, it reshaped the structure of the core itself. By conventional standards, it appears to be an endpoint. A structure formed by repeated mergers so extreme that gravitational growth has nearly exhausted what the local environment can provide. But then, the edges become uncertain. The outer halo of IC 1101 does not stop cleanly. Its faint starlight dissolves gradually into intra-cluster light, the diffuse population of stars drifting through the galaxy cluster itself. Some of those stars may once have belonged to smaller galaxies that were torn apart during mergers. Some may now be part of the cluster rather than the galaxy. The distinction is not obvious, and this matters. Because if the edge of a galaxy is not a line but a gradient, then the idea of measuring the largest galaxy becomes unstable. The record depends partly on where astronomers decide the galaxy ends. That alone would make the question difficult. But radio galaxies make it much stranger. Because now, the problem is no longer where a galaxy fades. It is whether its influence extends far beyond where its stars end. When astronomers discovered Alcyonius, the shock was not simply the size of the radio structure. It was the mismatch between the ordinary nature of the host galaxy and the extraordinary reach of its jets. An average-looking elliptical galaxy was somehow producing lobes of plasma extending 16 million light-years. That should not have happened so easily. Traditional intuition suggests bigger engines make bigger structures. Larger black hole, more energetic jets, greater reach. But Alcyonius disrupted that logic. Its black hole was not extreme. Its radio power was not extreme. Its host galaxy was not extreme. Yet, its structure was extreme. That forces a different explanation. Maybe the size of a galaxy's largest structures is not determined primarily by what the galaxy is. Maybe it is determined by what surrounds it. That is a profound shift, because it suggests the universe may produce colossal structures not by building more powerful galaxies, but by placing ordinary galaxies in unusually permissive environments. In a dense region, intergalactic gas pushes back. Jets slow. Loads remain confined. But in a sparse filament or near the edge of a cosmic void, resistance drops. The same jets can keep expanding and expanding and expanding. Suddenly, scale is no longer only a property of the source. It becomes partly a property of emptiness. And that idea overturns something subtle. We usually think empty space does nothing. But here, empty space may be what allows the largest structures to exist. Absence becomes architecture. Vacuum becomes a condition for scale. That alone changes how you think about the universe. But then Furion made it harder to dismiss as an anomaly. Because one record-breaking giant can be treated as a curiosity. 2 becomes a pattern. 3 becomes a population. And once LOFAR began identifying thousands of giant jet systems, the implication changed again. These structures were not rare accidents. They may be common. That creates the next turning point. If giant radio structures are common, then our previous picture of galaxies as isolated islands may have been incomplete all along. Because islands do not normally send magnetized plasma across tens of millions of light years. Islands do not inject energy into the cosmic web. Islands do not influence regions their stars will never reach. Something about the metaphor itself starts breaking. And once a metaphor breaks, the theory built around it often follows. A galaxy may not be merely a collection of stars. It may be a center of influence whose true extent depends on gravity, plasma physics, magnetic fields, and the surrounding structure of space-time itself. That is a much larger idea than the word galaxy was ever meant to hold. And it introduces a deeper discomfort. Because if galaxies can affect the cosmic web, then the cosmic web is not simply a background framework where galaxies form. It is part of a feedback system. Galaxies shape the web shapes galaxies. Both evolve together. And if that is true, then some of the largest structures in the universe may not be passive architecture at all. They may be partly self-modified. That possibility shifts the scale problem into something almost philosophical. Because we may have been separating objects from environment where no real separation exists. Perhaps the boundary between galaxy and universe was never as clean as we assumed. And once that possibility enters the picture, another question follows almost automatically. If a galaxy's influence can extend across a significant fraction of a cosmic void, what exactly counts as local anymore? If the boundary between a galaxy and its environment is uncertain, then the next question becomes unavoidable. How far can a single galaxy's influence actually reach before the word galaxy loses meaning altogether? For a long time, astronomers assumed there had to be practical limits. A black hole could launch jets. The jets could inflate radio lobes. Eventually, the surrounding medium would slow the expansion. Energy would dissipate. Growth would stop. That seemed reasonable. Every process in astrophysics appears to meet resistance somewhere. Stars exhaust fuel. Galaxies run out of gas. Clusters approach dynamical equilibrium. Even cosmic expansion has rules. So giant radio galaxies were once imagined as rare systems approaching a natural ceiling. But recent observations have made that ceiling harder to locate. Because every time the search deepens, the upper limit moves. That is not what a hard limit is supposed to do. A true boundary becomes clearer with better data. This one keeps retreating. And that changes the nature of the problem. The question is no longer where the largest known structure ends. It is whether the distribution has an end we can detect at all. That distinction matters, because if giant radio structures have no sharp upper cutoff, then the current record holders are not extreme exceptions. They may simply be the largest examples we have happened to notice so far. That is a very different situation. It means observational history may be masquerading as physical law. And science has seen this before. There was a time when the Milky Way was assumed to be the universe. Then it became one galaxy among many. There was a time when galaxy clusters seemed like the largest structures in existence. Then superclusters emerged, then filaments, then the cosmic web. Each expansion of observational reach forced a revision upward. The pattern is familiar, and now it may be happening again. Because once radio structures begin approaching scales comparable to cosmic voids, something unexpected appears. The old separation between galactic physics and cosmology starts to collapse. These were once treated as different domains. Galactic astronomy studied stars, black holes, mergers. Cosmology studied dark matter, large-scale structure, expansion. Different scales, different questions, different toolkits. But a radio structure spanning 23 million light-years does not respect that separation. It exists in both domains at once. Its origin is galactic. Its consequences are cosmological. That hybrid nature is one reason these discoveries have unsettled theorists. Because the object itself does not fit comfortably inside older categories. And when an object does not fit the categories, sometimes the categories are the problem. That leads to another shift. Maybe the largest galaxies are not merely bigger versions of ordinary galaxies. Maybe they belong to a different regime of behavior. A threshold where size changes what a system does. This happens elsewhere in physics. A small star behaves one way. A sufficiently massive star can collapse into a neutron star. Add more mass and it becomes a black hole. At each threshold, quantity becomes a change in kind. Perhaps galactic scale has thresholds too. Below one threshold, a galaxy mainly shapes itself. Beyond another, it begins shaping its cluster. Beyond another, perhaps it begins affecting the cosmic web. If so, then giant radio galaxies are not simply larger galaxies. They may be galaxies operating in a different phase, and that possibility carries an unexpected consequence. Because if some galaxies can alter the magnetization and thermal state of intergalactic space across enormous distances, then the large-scale universe may contain traces of ancient galactic activity embedded directly into its structure. Meaning some properties we treat as environmental background may actually be historical fingerprints. The medium between galaxies may remember, not consciously, not metaphorically, physically, in magnetic fields, in heated gas, in disturbed matter flows, a record written across millions of light years. That idea changes how emptiness looks. What seemed like empty intergalactic space may partly be fossil evidence. The aftermath of events so large, they altered the conditions through which later galaxies formed. And if that is true, then giant radio galaxies are not just curiosities at the edge of a size distribution. They may be participants in cosmic evolution itself. That was not the original expectation. The original question was simple: which galaxy is biggest? Now the question is becoming much stranger. How much of the universe may have been shaped by galaxies we barely understand? And this leads directly to one of the most uncomfortable implications in the entire story. If giant structures are common, if their influence can extend across cosmic scale distances, if many remain undetected, then some fraction of the universe may already be structured by processes we have only just recognized. Not unknown in principle, unknown in extent. And there is a difference. Unknown mechanisms suggest missing theory. Unknown extent suggests missing reality. That is harder to absorb, because it means the map may be incomplete not just in detail but in architecture. We may be underestimating how connected the universe really is. And if connection extends farther than we assumed, another assumption starts to weaken. The assumption that scale naturally produces isolation. Bigger structures should be farther apart, less interactive, more disconnected. That seems intuitive, but giant radio galaxies hint at the opposite. At sufficient scale, structures may become more entangled, not less, because their influence begins overlapping the framework that links everything else. That reverses the intuition completely. Instead of large scale producing detachment, large scale may produce deeper integration. And if that is true, then the largest galaxies may not be remote oddities at the edge of astronomy. They may be clues that the universe is more internally connected than our models have fully captured. Which raises a final problem. If the biggest structures we know keep growing larger with every improvement in observation, and if those structures may participate in shaping the cosmic web itself, then perhaps the real question was never how large a galaxy can become. Perhaps the real question is whether what we call a galaxy is only the visible core of something much harder to define. Something whose full extent we have not yet learned how to measure. If a galaxy may be only the visible core of something much harder to define, then the next step is not to ask how large these structures become. It is to ask whether our entire way of measuring cosmic structure has been too narrow. Because until now, every comparison in this story has relied on dimensions, diameters, halo radii, jet lengths, millions of light years. Distance has been treated as the language of scale. But what if distance is only one layer of size? That sounds abstract until you realize astronomy already uses multiple kinds of scale without always saying so. A galaxy has geometric size. It has mass. It has gravitational reach. It has energetic output. It has causal influence. These are not identical, and sometimes they diverge dramatically. The Milky Way is physically large. Its causal influence on the cosmic web is negligible. A giant radio galaxy may have a smaller stellar body than IC 1101, yet its energetic reach may extend much farther. Which one is larger? That depends on what kind of largeness matters. And once you admit multiple kinds of scale, the whole question becomes unstable again. Because a structure can be small in one dimension and enormous in another. That means the universe may not have a single hierarchy of size at all. It may have overlapping hierarchies, one for matter, one for energy, one for influence, and the largest objects may differ in each. That possibility changes how we think about records. Perhaps asking for the largest galaxy is like asking for the largest civilization by counting only land area while ignoring population, technology, or cultural reach. The answer tells you something, but not the whole story. And perhaps the most consequential structures in the universe are not necessarily the ones with the most stars. They may be the ones whose influence propagates furthest. That thought creates another turning point. Because if influence matters as much as extension, then black holes begin looking less like components inside galaxies and more like engines through which galaxies project themselves into the wider universe. That is a very different picture. A galaxy is no longer merely a gravitational container. It becomes partly a broadcasting system. Matter falls inward, energy moves outward. And through that exchange, the galaxy interacts with regions far beyond its visible body. That sounds almost metaphorical, but it is not. That is what the jets are doing. And once that becomes central, another assumption starts to fail. The assumption that galaxies are primarily defined by what they contain. Stars, gas, dark matter, contain mass, contain structure, contain boundaries. But giant radio galaxies suggest some systems may be defined just as much by what they export. Energy, magnetic fields, plasma, disturbance. Not contained properties, propagated ones. And if export becomes part of identity, then the meaning of a galaxy shifts. It becomes not just a thing, but a process. And processes do not have edges the way objects do. They fade, they overlap, they interact. That makes boundaries even harder. But it also points towards something larger. Because if galaxies are partly processes, then perhaps the cosmic web itself is not simply a static arrangement of matter. Perhaps it is partly an evolving network shaped by reciprocal activity among galaxies over billions of years. Not merely scaffolding, participation. And if that is true, the largest structures may not be individual objects at all. They may be relational structures, patterns produced by interaction. That possibility sounds subtle. Its implications are not. Because if some of what we call structure is really interaction spread across immense distances, then our inventories of cosmic objects may be missing something fundamental. We catalog galaxies, we catalog clusters, we catalog filaments. But what if some important realities are not objects to catalog, but processes to trace? That would mean our maps show locations, while partly omitting dynamics. And dynamics may be where the deeper story lives. This becomes especially unsettling when you consider time, because every giant structure we observe is historical. We do not see it as it is. We see ancient light, ancient radio emission, ancient states of matter. Furion existed as we observe it when the universe was far younger. What happened to it after the light left? Did the jets expand further? Did they fade? Did the host galaxy evolve into something even stranger? We do not know. And that ignorance matters. Because the largest structures we have measured may not represent completed structures. They may be snapshots of things still growing. That possibility alters the emotional weight of the entire question. We have been asking, what is the largest galaxy ever found? But perhaps some of these structures were larger later than when we observed them. Perhaps the largest we have measured was not the largest it became. Now, the record itself depends partly on cosmic timing, not just size, not just definition, but when in a structure's history we happen to intercept its light. That makes the question even less closed than it seemed, and it produces a deeper consequence. Maybe there is no final record in principle, not because observations are incomplete, but because the things being ranked may themselves be evolving while we rank them. A moving distribution of moving structures. That is much harder to reduce to a title. And this is where the problem stops being merely astronomical. It starts becoming epistemological. A question about the limits of how we know what we know. Because every framework we have used so far assumes reality can be divided into units stable enough to compare. Galaxy A, Galaxy B. Which is bigger? But if boundaries blur, if influence matters, if processes matter, if structures evolve after the light we receive, then the units themselves become unstable, and comparison starts losing its foundation. That does not mean the science fails. It means the phenomenon may be richer than the categories built to contain it. And science advances precisely at those moments, when the categories strain, when the old language no longer fits, when something real refuses to remain inside the concepts invented to describe it. That may be where giant galaxies have brought us. Not to the upper limit of size, but to the edge of a definition. And once a definition begins breaking down, a deeper possibility appears. Perhaps the largest structures in the universe are difficult to identify, not because they are hidden, but because we are still looking for them as objects, when they may have to be understood as something else entirely. If the largest structures may have to be understood as something other than isolated objects, then a more difficult question appears. What if the real limit we keep encountering is not a limit in the universe, but a limit in the way the human mind organizes reality? Because throughout this story, one pattern has repeated. Every time the scale expands, the categories weaken. Galaxy, cluster, filament, void. Each seem distinct, then observations revealed overlap. Edges blurred, definitions softened, boundaries became negotiable. That is not merely a scientific inconvenience. It suggests the universe may not be organized according to the discrete objects our thinking prefers. That possibility is unsettling, because object-based thinking runs very deep. Human cognition depends on separating things. This is one entity, that is another. This begins here, that ends there. Without boundaries, ordinary reasoning struggles. But nature often ignores the boundaries that thought imposes. A coastline has no precise edge at every scale. A cloud has no exact perimeter. Even a living organism is in constant exchange with its environment. And now, galaxies may be forcing the same realization at cosmic scale. Perhaps what we call objects are often only concentrations within continuous processes. That sounds philosophical, but it may be physically necessary. Because consider what happens if a giant radio galaxy injects magnetized plasma into intergalactic space, altering conditions in regions where later galaxies form. The distinction between source and environment becomes historically entangled. The environment is partly shaped by earlier sources. Future sources emerge inside that altered environment, and the cycle continues. That is not a collection of isolated objects. That is a coupled system. And coupled systems behave differently. They can generate patterns no individual component predicts. Feedback, emergence, self-organization. These concepts appear in climate systems, in ecosystems, in neural networks. Perhaps they belong at cosmic scale too. If so, then the largest galactic structures may not simply challenge the size record. They may hint that the universe has a deeper level of organization than our traditional picture captured. That is a much bigger claim. And it creates another intellectual pivot. Because if large-scale cosmic structure involves feedback and emergent behavior, then asking only how big a galaxy becomes may be like asking how large a neuron is while ignoring the brain. The question may not be wrong, but it may be too local. And once that possibility enters, the story changes again. The biggest structures may matter less as isolated extremes than as clues about larger systems we do not yet fully recognize. That idea becomes even more provocative when you consider magnetism. Magnetic fields are often treated as secondary details, but they influence particle motion. They affect gas dynamics. They shape plasma behavior. They may help regulate how matter moves through cosmic environments. And if giant radio galaxies help seed or amplify magnetism across enormous regions, then they may be contributing to a hidden layer of cosmic structure not obvious in ordinary maps. Because maps of galaxies show matter. Maps of dark matter show gravitational scaffolding. But a map of cosmic magnetism may reveal another architecture layered across both, an invisible structure braided through the visible one. And if galaxies help generate that layer, then their true influence may be underestimated even now. That possibility carries a strange implication. Some of the universe's largest structures may be partly invisible, not because they emit no light, but because their most consequential effects are distributed through fields rather than objects. That is much harder to picture, but perhaps that is exactly why it matters. Because human intuition is comfortable with things, less comfortable with fields. Yet modern physics keeps moving toward fields. Gravity as space-time geometry, electromagnetism as field behavior, quantum theory built on fields. And now, perhaps even the story of giant galaxies points in that direction. Less about isolated matter, more about distributed influence. That is not where the story began. It began with a simple curiosity about the largest galaxy. And now, it is approaching a question about whether the universe is structured less like a collection of objects and more like overlapping domains of influence. That is a much stranger possibility, and it raises another problem. If reality at large scales is organized partly through overlapping influence rather than discrete containment, then perhaps our search for maxima, for the largest galaxy, largest cluster, largest structure, may reflect a habit of ranking reality in ways nature itself does not privilege. Perhaps the universe does not care about biggest. Perhaps it expresses distributions, transitions, regimes, relationships. And perhaps what we call records are temporary landmarks inside those deeper patterns. That thought changes how future discoveries look. If SKA discovers radio structures spanning 40 million light years, Would that be shocking? Or would it simply reveal that our current expectations were too small? And if it finds no hard cutoff at all, what would that imply about the possible scales astrophysical processes can reach? Because without a detectable ceiling, something deeply uncomfortable follows. The upper range may not be bounded in any way we currently understand. Not infinite, but open. And open systems are psychologically difficult. They deny closure. They refuse final answers. They keep the horizon receding. That is exactly what has happened throughout this entire story. Every attempt to define the largest galaxy produced a larger context. The Milky Way led to giant ellipticals. Giant ellipticals led to radio giants. Radio giants led to cosmic web interactions. And those interactions may now point toward deeper systemic organization. Each answer dissolved into a bigger question. That pattern itself may be the most important clue. Because sometimes what keeps expanding is not just the subject being studied, but the framework required to study it. And when that happens, science is often approaching a conceptual threshold, a point where discovery stops adding details to an existing picture and starts changing the picture. Perhaps giant galaxies represent such a threshold, not because they are merely enormous, but because they force us to ask whether the universe at its largest scales behaves less like a set of separate structures and more like a continuous system whose major components only appear separate from the limited perspective of observers embedded inside one small spiral galaxy. And if that possibility is even partly true, then the real question may no longer be how large a galaxy can become, but whether what we have been calling galaxies are only the visible nodes of a much larger cosmic process we have barely begun to recognize.